Hello, I'm Miss Ginsburg with KnowAtom, and today we're going to be reading Earth in Space. This is a lab manual in Unit 2. Section 1, Patterns in Movement, Experimenting in Space. On March 1st, 2016, an astronaut named Scott Kelly returned to Earth. He had just spent 340 days in space, orbiting Earth in the International Space Station. The space station is a moving science laboratory that orbits 386 kilometers, or 240 miles, above Earth. To orbit means to travel in a circle around an object. Astronauts from around the world live together on the space station for months at a time. The space station orbits Earth once every 90 minutes. From space, Scott saw more than 10,000 sunrises and sunsets. He took more than 1,000 photographs. Scientists on the space station are busy conducting a variety of different experiments. One question that Scott Kelly was helping to investigate was how life in space affects human health. Scientists are trying to answer this question with an eye toward human exploration of the planet Mars. Mars is so much farther away from Earth than the space station that a trip to Mars will require a much longer time in space. Scientists are particularly interested in the effects of the low-gravity environment of space. Gravity is a force of attraction between all matter. A force is a push or pull that acts on an object, changing its speed, direction, or shape. Because it is an attractive force, gravity pulls objects toward one another. Scott Kelly had an unusual control in his experiments. He has an identical twin brother, Mark, who stayed on Earth while Scott was in space. Because Mark and Scott are identical twins, they have an almost identical genetic makeup. This allows scientists to compare the two brothers to try to determine the long-term effects of a low-gravity environment on the human body. So here's Mark, and there's Scott, and they're identical twins. Here on Earth, you always experience the pull of Earth's gravity. It pulls all objects on or near its surface down toward the planet's center. The effects of gravity are different on the International Space Station from how they are on Earth. There is much less gravity on the space station than on Earth. It is because of this low gravity that astronauts float in space and why they can lift objects that weigh hundreds of pounds. Low gravity also affects the muscles of astronauts. On Earth, we have to use our muscles just to stand up against the force of gravity, which is constantly pulling on us. This requires our bodies to maintain enough muscle to support our own weight. In the low-gravity environment of space, astronauts lose muscle since it is not required to support their weight. To counter this, astronauts have to exercise regularly. One experiment that Scott Kelly was part of on the space station was investigating how a low-gravity environment affects a person's muscle mass over an extended period of time. As soon as Scott returned to Earth, he and Mark began a series of tests by different scientists who are looking for differences between the brothers. There isn't a quick answer to this question. Scientists plan to continue to study the Kelly brothers over time to answer the question of whether there are any long-term effects that don't show up right away. The low gravity of the space station occurs because the space station is actually in free fall around Earth. Because of Earth's gravitational pull, the space station is constantly falling toward Earth's surface, in the same way that a pen you throw up in the air falls back to the ground. Astronauts exercise regularly on the space station. However, the space station is also moving at 28,164 kilometers, or 17,500 miles per hour. It moves at a speed that matches the way Earth's surface curves. Because of this, the spacecraft keeps falling toward Earth's surface, but never hits it. This happens because of two interacting factors, gravity and inertia. Gravity is a result of an object's mass. All matter has gravity. Dust has gravity. Rocks have gravity. Even people have gravity. Objects don't orbit us, however, because we don't have enough mass. The more massive an object is, the more its gravity will pull on other objects and cause them to move. Because gravity is an attractive force, objects don't need to come into contact with one another to exert a force on each other. Instead, objects have gravitational fields. A gravitational field is the area around one object where another object will feel the gravitational force of the first object. Earth is so much more massive than the space station that its gravitational field extends beyond the space station, pulling it toward Earth's center. Gravity exists because matter changes space. Picture Earth as a large bowling ball sitting on a blanket. If a marble, the space station, is placed near the depression the bowling ball, Earth, creates, the marble will move toward it. This gravitational field causes patterns in movement. Remember that a pattern is something that happens in a regular and repeated way. Every time you release a pen in the air, the pen will fall back to Earth's surface because the pen is within Earth's gravitational field. Anything within Earth's gravitational field will feel Earth's gravitational force. Gravity and motion. The force of Earth's gravity doesn't pull the space station down to Earth's surface because all objects in orbit are also moving sideways at approximately 90 degrees to the force of gravity. If Earth's gravitational field didn't exist, the space station would travel in a straight line because of inertia. We'll explore inertia more later on, but for now, remember that inertia is the tendency of an object at rest to remain at rest, and an object in motion to remain in motion unless acted on by an outside force. Earth's gravity provides the outside force that changes the space station's motion. Earth's gravitational field is so strong that its attractive force changes the motion of the objects within its field to an orbit around it. Picture a ball on the end of a string. If you swing the string around, the ball is constantly being pulled toward your hand, just as Earth's gravity pulls the space station toward it. But the ball's sideways motion around the string keeps it moving so it doesn't fall to the center. Without that pull to the center, for example, if you let go of the string, the ball would go flying off in a straight line away from you. The space station isn't the only object orbiting Earth. The moon is also pulled into orbit around Earth because of the moon's motion and the force of gravity. Earth's gravity changes the motion of the space station, pulling it into orbit. Earth's Sun-Moon system. As the moon and the space station orbit Earth, Earth itself is in motion, orbiting the sun. The sun is so much more massive than Earth that more than 1 million Earths could fit inside the sun. Because of the sun's mass, the sun's gravitational field pulls Earth into orbit around it. The space station and the moon orbit Earth and not the sun because the force of gravity becomes weaker as the distance between two objects increases. The moon and the space station are much closer to Earth than they are to the sun, so Earth's gravity is the dominant force on them. This is also why we all experience the downward pull of Earth's gravity. As Earth orbits the sun and the moon orbits Earth, these three objects form a system because they interact with one another. Remember that a system is a set of connected, interacting parts that form a more complex whole. The moon orbits Earth, and Earth orbits the sun in a regular, predictable way. For example, it takes the moon 29.5 days to complete one orbit around Earth. This is equal to 1 month. And it takes Earth 365 days to complete one orbit around the sun. This is equal to 1 year. The sun, Earth, and moon form a system because they interact with and influence one another. The motion of the moon around Earth and the Earth-Moon system around the sun results in predictable patterns of movement. Seasons. As Earth moves around the sun, the amount of sunlight that reaches the planet changes over a year. This causes seasons, periods of time characterized by specific weather patterns and by the length of day and night. People often believe that Earth has seasons because Earth is closest to the sun in the summer, and this is why the summer is so much hotter than the winter. However, this isn't true. The distance between Earth and the sun is relatively constant during Earth's orbit. The reason that the Earth experiences seasons has to do with the planet's tilt on its axis as it orbits the sun. The axis is an imaginary line that goes from the North Pole to the South Pole. Earth is tilted 23.5 degrees on its axis. As Earth orbits the sun, its tilted axis always points in the same direction, toward the North Star. So different parts of Earth get the sun's direct rays throughout the year. For half of the year, Earth's North Pole is tilted toward the sun. When the North Pole is tilted toward the sun shines more directly on the northern hemisphere. This is because the sun's rays hit Earth at a higher angle. This causes temperatures to be warmer. At the same time, the sun is shining less directly on the southern hemisphere. This is because the sun's rays are hitting Earth at a lower angle. This causes the sun's rays to spread out over more space, which results in cooler temperatures. This results in summer in the north and winter in the south. For the other half of the year, Earth's North Pole is tilted away from the sun. This results in winter in the north and summer in the south. The point when the North Pole is in between a full tilt toward or away from the sun creates the seasons of spring and fall. Earth's tilt also causes seasons to differ depending on where you are on the planet. This is because of Earth's curved shape. The sun's rays are the most concentrated around the equator, which causes temperatures to be high. Moving north or south of the equator, the sun's rays are spread over a larger area, so each square meter of Earth's surface receives less solar energy. As a result, these regions have lower temperatures. Seasons occur cyclically, which means they occur once in a set period of time. Each season occurs once every year because that is how long it takes the planet to complete one full orbit around the sun. At the same time as Earth is orbiting the sun, it is also spinning on its axis. Earth completely rotates around its axis once every 23 hours and 56 minutes. This is a day because of how the sun shines on Earth as it rotates. As Earth rotates, part of the planet gets light and then dark. The sun always shines, but its light only hits one half of the planet at a time. The sun's rays hit Earth more directly at the equator. This causes warmer overall temperatures. Earth's rotation causes day and night. Interaction of the Earth-Sun-Moon system also result in predictable patterns in how the moon appears from Earth as it travels across the night sky. These patterns in movement happen because of the moon's position in space relative to Earth and the sun. At the same time as Earth's gravity pulls the moon into orbit around it, the moon is also rotating on its axis. The same side of the moon always faces Earth because it takes the moon the same amount of time to complete one rotation as it does to complete one orbit around Earth. This also means that one day on the moon equals about 13 days on Earth. It is because of the sun that we can see the moon at all. The moon doesn't emit its own light. Instead, we see the moon because the sun shines on it, lighting it up for us. Exactly half of the moon is always in sunlight, but we don't always see the entire sunlit portion. The same side of the moon always faces Earth, but we don't always see the entire part of the moon that is facing Earth. The part of the moon that we see depends on where the moon is in its orbit around Earth. Within a month, the part of the moon that we see from Earth changes from a full white disk in the sky to a small sliver, and then back to a full white disk. These changes are called phases. There are 8 phases in the moon cycle. The changing appearance of the moon as seen from Earth as it orbits Earth. We always see the same side of the moon because the moon orbits Earth at the same rate as it rotates on its axis. The moon appears to change shape because of where the moon is in its orbit relative to Earth and the sun. Moon phases. New moon is the first phase in the moon cycle when the moon is positioned between Earth and the sun. The entire half of the moon lit by the sun is facing away from Earth, so the moon is not visible from Earth. After new moon, the part of the moon lit by the sun increases, but it is still less than half. This is the waxing crescent phase of the moon cycle. As the moon continues its orbit, it reaches a point where it is at a 90-degree angle relative to Earth and the sun. This is the first quarter of the moon cycle. From Earth, the left half of the moon appears unlit and the right half of the moon appears lit. After the first quarter, the sunlit part of the moon continues to increase. This is called the waxing gibbous phase of the moon cycle. When the moon reaches the opposite side of Earth, we see a full moon from Earth, where it appears round and bright. The moon, Earth, and the sun are lined up similarly to new moon, but the moon is on the opposite side of Earth. As a result, the entire half of the moon that receives sunlight is facing Earth. After full moon, the sunlit part of the moon begins to decrease. The waning gibbous phase occurs when more than half of the moon is lit by the sun, but the lit part is decreasing. As the moon continues its orbit, it again reaches a point where it is at a 90-degree angle relative to Earth from the sun. This is the third quarter. From Earth, the left half of the moon appears lit, and the right half of the moon appears unlit. Following the third quarter is the waning crescent, which wanes until the light is completely gone, beginning the cycle again with new moon. Here are the phases of the moon as viewed from Earth. Eclipses. In early March 2016, scientists were excitedly getting ready for a rare event, a total solar eclipse. An eclipse occurs when one object in the solar system moves into the shadow of another object. There are two kinds of eclipses on Earth, an eclipse of the sun and an eclipse of the moon. A solar eclipse occurs when the moon moves between the sun and Earth. When this happens, the moon blocks the sun's light from reaching Earth. A solar eclipse can only occur during the new moon phase of the moon cycle, when the moon passes between Earth and the sun. If the moon's shadow falls on Earth during new moon, it appears that the sun has become completely dark. There are different types of solar eclipses. For example, a partial solar eclipse happens when the sun, moon, and Earth are not exactly lined up. The sun appears to have a dark shadow on only a small part of its surface. The rarest is a total solar eclipse. For a total eclipse to take place, the sun, moon, and Earth must be in a direct line. Scientists were excited about the March 2016 solar eclipse because total solar eclipses are so rare. They also provide scientists with the opportunity to study parts of the sun that they usually cannot. The sun is so bright and hot that we cannot send instruments to the sun or gather samples of the sun to study back on Earth. During a total solar eclipse, a part of the sun that isn't usually visible becomes visible from Earth. This part is called the corona. It is the sun's outer atmosphere. The corona is where solar weather, such as solar wind, takes place. This solar weather affects the entire solar system, including scientific instruments in space. One goal of studying the corona is to be able to predict solar weather in the same way that scientists predict weather on Earth. In contrast to solar eclipses, lunar eclipses occur when Earth moves between the sun and the moon. During a lunar eclipse, Earth blocks the sun's light that normally reflects off of the moon. Lunar eclipses can only occur during the full moon when the moon passes through Earth's shadow. The moon does not completely disappear during a lunar eclipse. Instead, it appears reddish. This is because light from the sun must first pass through a long and dense layer of the Earth's atmosphere before it reaches the moon. Just like the solar eclipse, lunar eclipses do not occur every full moon. Scientists are also interested in lunar eclipses because they can get some unique information about the moon. For example, in 2011, scientists collected data about how the temperature of the moon's surface changes during a lunar eclipse. This is interesting to scientists because the moon generally takes a longer time to move from day to night since its rotation is relatively slow. However, during a lunar eclipse, the moon moves rapidly from being in direct sunlight to complete shadow. They learned that the temperature changes by 260 degrees Celsius, or 500 degrees Fahrenheit. Solar and lunar eclipses do not happen every month because the moon's orbit around Earth is tilted 5 degrees. As a result, the alignment of Earth, the moon, and sun only occurs about once every 6 months. Earth blocks some of sun's light during a lunar eclipse. The moon's orbit around Earth is tilted compared to Earth's orbit around the sun. Section 2. Exploring the solar system. Looking for life beyond Earth. Since August 2012, a science laboratory the size of a car has been exploring the surface of Mars. This laboratory is actually a rover called Curiosity. A rover is a robot that drives around. Curiosity has been busy since it first landed. It has drilled holes, collected rock samples, and taken pictures of its surroundings. Curiosity has a wide range of scientific instruments. For example, it has a 2-meter or 7-foot arm that can pick up samples from the surface. Once inside the rover, those samples can be heated. The rover can then sniff the gases that are released. It does this to look for clues about how the rocks and soil formed. The mission of Curiosity is to study the Martian climate and geology. Geology is the study of a planet's structure, as well as the processes that have shaped it. The goal of the mission is to determine whether Mars has ever been able to support life. Curiosity is just one way that scientists are gathering data about Mars. Mars is the most explored planet beyond Earth. This is because scientists want to send humans to Mars in the future. In addition to Curiosity, there is another rover called Opportunity, collecting data from the planet's surface. There are also 3 NASA spacecraft orbiting Mars. These spacecraft are collecting data about the planet's climate and structure. NASA is the U.S. agency that is responsible for science and technology related to air and space. This is a selfie taken by Curiosity on Mars. And here's a picture of Mars. Earth's place in the solar system. Before humans can travel to Mars, they need to learn more about the planet and how it will be able to support life. There are several reasons that scientists are focused on Mars. It is Earth's second closest planetary neighbor in space. Both Earth and Mars are part of a solar system, a collection of planets and other objects that orbit a sun. A sun is the star at the center of a solar system. Our solar system is made up of 8 known planets: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. A planet is a body that orbits the sun, is massive enough for its own gravity to make it round, and has cleared out smaller objects around its orbit. All of the matter in the universe, including all of the planets, is made up of the same elements that form all matter on Earth. Like Earth, Mars is a terrestrial planet. This means that it has a rocky surface. There are 2 other terrestrial planets, Mercury and Venus. Earth is the 3rd planet from the Sun, and Mars is the 4th. Terrestrial planets all have a similar internal structure. They all have a central core made up of mostly iron, a mantle that surrounds the core, and a rocky surface with canyons, craters, mountains, and volcanoes. These planets also have a few, if any, moons. The other 4 known planets are Jupiter, Saturn, Uranus, and Neptune. They are called gas giants. They are much more massive than the terrestrial planets. However, they are less dense than the terrestrial planets because they are made up almost entirely of gas. The gas giants are orbited by many moons and colorful rings made of rock, dust, and ice. In January 2016, scientists announced that they found evidence of a 9th planet far beyond Neptune, but that hasn't yet been confirmed. Scale in the solar system. The solar system is so massive that scientists use scale models to understand the distances and sizes of the planets relative to each other. Remember that scale is the size, extent, or importance, magnitude, of something relative to something else. However, there is such a difference in size and distance between the different objects in the solar system that no one model can show everything. So scientists often compare planets using one scale property at a time. One way to compare planets is distance from the sun. Our sun is much closer to Earth than any other star. In Earth terms, however, it is still very far away. It is 150 million kilometers, or 93 million miles away from Earth. At this distance, it takes sunlight 8 minutes to travel from the sun's surface to Earth. Mars is 229 million kilometers, or 142 million miles from the sun. Neptune, the farthest planet from the sun, is much farther. It is 4.5 billion kilometers, or 2.8 billion miles from the sun. Scale is also helpful when thinking about the size of different objects in the solar system. For example, the sun is the most massive object in our solar system. Its diameter is 1.4 million kilometers, or 865,000 miles wide. In comparison, Earth's diameter is 12,756 kilometers, or 7,926 miles. Mars is only 10% as massive as Earth, with a diameter of 6,792 kilometers, or 4,220 miles. If the sun were the size of a typical front door, Earth would be about the size of a nickel. Jupiter, the largest planet in our solar system, would be the size of a basketball. Mercury, the smallest planet, would be the size of a pea. So this is a scale model of the solar system. The search for water. Another property is temperature. On Mercury, which is the closest planet to the sun, temperatures can reach 427 degrees Celsius, or 801 degrees Fahrenheit. On Neptune, the farthest planet from the sun, temperatures can reach negative 218 degrees Celsius, or negative 360 degrees Fahrenheit. Earth has an average temperature of 14 degrees Celsius, or 57 degrees Fahrenheit. Earth's temperature allows for another difference from any of the other planets. Earth is unique because, unlike any other known planet, water is found almost everywhere on Earth, in all 3 states. Water molecules make up the ice found in glaciers and snow, the liquid water in oceans, lakes, and rivers, and the water vapor gas in Earth's atmosphere. Water is able to exist in all 3 states because of Earth's temperature. Any closer, and the sun would cause temperatures to be too high. Any farther away, and the temperature would be too low. Scientists have known that solid water, or ice, is present on Mars and throughout the solar system. Scientists believe that Mars' permanent northern ice cap is mostly frozen water, while the southern cap is made up of frozen water and carbon dioxide. However, curiosity has been searching for liquid water on Mars because it is necessary for almost every known living thing. Without water, there would be no life on Earth. In September 2015, scientists announced that they had found evidence that liquid water does indeed sometimes flow on Mars. It took multiple spacecraft over several years to solve this mystery. Now we know there is liquid water on the surface of this cold, desert planet, said NASA scientist Michael Meyer. It seems that the more we study Mars, the more we learn how life could be supported and where there are resources to support life in the future. Scientists have been looking for liquid water on Mars. Ice, liquid water, and water vapor all exist on Earth. Patterns in planets. The evidence of liquid water comes from dark streaks in gullies and craters on Mars. Scientists believe the streaks are caused by salty water, but they still aren't sure where the salty water comes from. On Earth, the majority of the planet is covered by oceans filled with salt water. The surface of Mars, in contrast, is mostly covered by red dust. This red dust gives the planet its nickname of the red planet. These dark streaks only appear in the summer. Mars experiences the same 4 seasons that Earth does: summer, fall, winter, and spring. This is because Mars has a very similar tilt to Earth at 25.2 degrees on its axis. However, Mars is farther away from the sun. Because of this, it takes almost twice as long for Mars to complete one orbit around the sun, 687 Earth days. As a result, seasons on Mars last longer than seasons on Earth. All of the planets have seasons. As the planets orbit the sun, different amounts of sunlight reach different parts of the planet at various times throughout the orbit. Every planet is tilted on its axis, but each planet is tilted at a different angle. For example, Jupiter has almost no tilt at 3 degrees. Because of this, Jupiter experiences very little change between its seasons. However, Jupiter is much farther from the Sun than Earth is. As a result, the length of each season is about 3 Jupiter years, compared to 3 months on Earth. In contrast to Jupiter, Venus has an almost 180-degree tilt, which means Venus is spinning upside down. Uranus has a 90-degree tilt, which means it is spinning on its side. And each planet has a different orbit because of its distance from the Sun. For example, Mercury has the shortest orbit, taking just 88 Earth days to complete its turn around the Sun. Neptune has the longest orbit because it is farthest from the Sun. Its orbit takes 164.8 years, or 60,182 Earth days. Scientists believe these dark streaks were formed by flowing liquid water. This image is created using false colors to show the streaks. There are also patterns in the length of a planet's day and night. Like Earth, all planets rotate on their axis. Earth and Mars have about the same length of one day because their rotation speed is very similar. It takes Mars 24 hours and 40 minutes to complete one rotation. This is one day on Mars, which is also called a sol. It is very close to Earth's rotation of 23.5 hours. In contrast, the gas giants rotate much faster than any of the terrestrial planets. It takes Jupiter just 10 hours to complete one rotation. Venus has the slowest rotation, taking 5,832 hours to rotate once. Every planet in the solar system is held in its orbit by the force of the Sun's gravity. The distance a planet is from the Sun determines how strong the Sun's gravity will pull on the planet. Planets that are closer to the Sun experience a stronger pull of the Sun's gravity than planets that are farther away. In addition to the planets, the Sun is also orbited by non-planets. The asteroid belt between Mars and Jupiter is made up of rocks left over from planets that didn't form. Comets are small objects made up of mostly ice and dust, and they are usually found farther from the Sun. Planet-like masses called dwarf planets are also found throughout our solar system. Pluto, Ceres, and Charon are examples of dwarf planets. Each of the planets has its own gravity that is determined by its mass. This is why some planets are orbited by moons. Earth is orbited by just one moon, while Mars is orbited by 2 moons. Jupiter has so much mass that it holds in orbit the most moons of any planet. Jupiter is so large that all of the other planets in the solar system could fit inside it. More than 1,000 Earths could fit inside Jupiter. Here's a picture of Earth compared to Jupiter. Planet mass and gravity. The gravitational force exerted on an object by a planet or moon is called weight. In science, mass and weight are not the same, even though here on Earth, the distinction between mass and weight is typically ignored by non-scientists. This is because acceleration due to gravity is nearly identical everywhere on Earth, except with highly sensitive instruments. On other planets, which have noticeably different gravities, an object's weight would change dramatically. It would more than double on Jupiter, which has the highest gravity. That same object's weight would drop by 85% on the Moon. The object's mass, on the other hand, would remain the same regardless of where it was. Mars' weaker gravity allows for a unique surface feature. Mars has the largest volcano in our solar system called Olympus Mons. Olympus Mons is 24 kilometers high and measures 550 kilometers across. By comparison, Earth's largest volcano, Mauna Loa in Hawaii, raises 9 kilometers high and measures 120 kilometers across. Olympus Mons could not exist on Earth. Earth's stronger gravitational pull would cause the massive volcano to collapse under its own weight if it were here. An object's weight depends on the force of gravity. Olympus Mons compared to the state of Arizona. Gravity in the universe. It has taken humans about 4 days to travel from Earth to the Moon. NASA predicts that it will take at least 8 months for a spacecraft with astronauts to travel from Earth to Mars, although scientists are trying to speed up that time. It took 33 years for a space probe called Voyager 1 to reach the edge of our solar system. Voyager 1 is now beyond our solar system in the physical space of the Milky Way galaxy. A galaxy is a large cluster of stars held together by gravity and separated by unimaginable distances of space. Just as the 8 planets of our solar system orbit the Sun, our entire solar system is in orbit around the center of the Milky Way galaxy. This occurs for the same reason that the Moon orbits Earth and the Moon-Earth system orbits the Sun. The center of the Milky Way galaxy has a much larger mass than our solar system or the other stars and systems within the galaxy. So its gravitational force pulls all of the stars within the galaxy into orbit around it. Our solar system is located near the edge of the Milky Way galaxy, which gets its name because of its faint white appearance in the sky that looks like spilled milk. The Milky Way galaxy is shaped like a thick pancake and contains more than 200 billion stars, including our Sun. And the Milky Way galaxy is just one of about 100 billion galaxies in the universe. The universe is the wide open space that holds all matter and energy known to exist. There is constant motion in the universe because of gravity's attractive pull. Section 3. STEM in space. Building the International Space Station. The International Space Station is slightly larger than an American football field. It is so large that it had to be built in space. The first piece was launched in 1998, and it wasn't finished until 2011. However, people began living on it in 2000. The space station had to be built piece by piece in space because there is no rocket powerful enough to launch the entire station into space at one time. The completed space station has a mass of almost 453,592 kilograms, or 1 million pounds. Scientists and engineers had to send the separate parts of the space station on rockets. It took more than 40 missions to get all of the materials into space and assembled. Engineers who design rockets to launch into space apply 3 basic laws of motion that describe how forces cause objects to move. These 3 laws were first described by a scientist named Sir Isaac Newton in the 1600s. Newton was fascinated by how things move. After much study, he realized that the motion of all objects followed the same 3 basic laws. Newton's first law of motion describes inertia. Remember the motion of planets and how they would keep moving in a straight line if it weren't for the pull of gravity? Newton observed that when all of the forces acting on an object are balanced, the object will not change its motion. When the forces acting on an object are equal, they are balanced. Stationary objects won't start moving, and moving objects won't start moving unless the forces pushing or pulling on these objects become unbalanced. Unbalanced forces occur when 2 opposing forces act on an object are not equal. Forces and motion. In order for the space rocket to be launched, it needs an unbalanced force to cause it to move. Unbalanced forces cause movement because they transfer energy into or out of objects or systems. Remember that energy is the ability to do work. When an unbalanced force is applied to an object, energy transfers to that object. This transfer of energy changes the motion of the object. Imagine that a ball is sitting at the top of a hill. Because of its position on the hill, the ball has a form of potential energy called gravitational energy. Gravitational energy is the energy stored in an object as a result of its vertical position or height. If someone comes along and pushes the ball, that person applies a force to the ball that transfers kinetic energy to the ball. The ball now has kinetic energy, which is what powers its movement from the top of the hill to the bottom of the hill. If no other forces acted on the ball once it started moving, it would continue moving because of inertia. However, there are other forces acting on the ball that cause it to eventually slow down. For example, friction is a force that slows motion when two objects rub against each other. Friction slows motion because it causes some of the energy of the moving object to change into heat. Friction is why your hands feel hot after you rub them together. Drag, also called air resistance, is similar to friction, except that it occurs between a solid substance and a fluid, such as air. These same principles that cause the ball to move apply to rockets. Because of this, engineers launching rockets need to apply an unbalanced force on the rocket to cause it to begin to move. However, engineers also need to think about the mass of the rocket they are launching. This takes us to Newton's second law, which says that the amount of force needed to move an object any distance depends on its mass. It is written as an equation: force equals mass times acceleration. Acceleration is an increase in speed over time. It is measured in meters per second squared. Speed is the rate at which an object covers distance in a period of time. It is measured in meters per second. In other words, the more massive the rocket is, the more force will be required to change its motion and launch it into space. This is because the kinetic energy of an object is proportional to its mass. Remember that kinetic energy is the energy of motion. Proportion refers to the relationship between things as to size, quantity, or number. The kinetic energy doubles as the mass of the object doubles, while the kinetic energy halves as the mass of the object halves. Newton's second law can be understood in two ways. The first is to think about what would happen if you have two objects of different masses. For example, imagine that engineers are testing a rocket with a massive piece of space equipment and the same rocket with a less massive piece of equipment. If the same amount of force is applied to both rockets, the one with the less massive equipment will travel farther than the one with the more massive equipment. Now, imagine that those same engineers are testing one rocket with a piece of equipment, but now they are applying different amounts of force. When a small force is applied, less energy will be transferred to the rocket. This will cause the rocket to travel a shorter distance and more slowly, because it has less kinetic energy. If a greater force is applied to the rocket, more energy will be transferred to the rocket. This will cause the rocket to travel farther and faster because it has more kinetic energy. Newton's third law is the action-reaction law. This law states that for every action, there is an equal and opposite reaction. Action-reaction pairs occur whenever two objects come into contact with each other. You are experiencing action-reaction forces right now. Remember that gravity is constantly pulling down on you. In reaction to the force of gravity pulling down, the ground has its own force that pushes back up with the same amount of force. This keeps you from sinking into the ground. If the ground did not push back with the same amount of force, you would fall into the ground. In this case, the forces would be unbalanced. Gravity would pull you down with a greater force than the force of the ground pushing back up. A deflating balloon is another example of action-reaction forces. As the air escapes out the open end of a balloon, the force causing the rest of the balloon to move forward with an equal and opposite force. Rockets are designed to move because of action-reaction forces. The rocket pushes combustion exhaust downward, the action. This is also called thrust. In reaction, the exhaust pushes the rocket upward. Because of Newton's second law, the greater the thrust, the more the rocket will accelerate upwards. Similarly, the more massive the rocket is, the more powerful the thrust will need to be. This is why the International Space Station couldn't be launched after it was already built. There is no rocket that can produce a powerful enough thrust to get an object that massive into space. Rockets use action-reaction forces to move. Transferring energy. Once the rocket begins to move, it will continue to move until another force acts on it to slow it down or stop it. On Earth, gravity pulls down on the rocket. The rocket also experiences drag as it moves through the air. Drag acts on an object in the opposite direction as the movement. Because of this, the rocket must produce enough thrust to counter Earth's gravity and the air's drag. The amount of thrust needed depends on the rocket's mission. If it is to explore Mars, for example, the rocket needs enough thrust to move beyond Earth's gravitational field entirely. However, rockets heading to the International Space Station need enough thrust to move into space, but not so much that they leave Earth's gravitational field. With the right amount of force, the rocket can begin to orbit Earth. Once rockets carrying spacecraft are successfully launched into space, astronauts must be very aware of space debris. More than 500,000 pieces of space debris orbit Earth. Some of the debris is also natural, such as meteoroids. However, the most common space debris orbiting Earth comes from human-made sources, including old spacecraft that are no longer in use. These objects travel at speeds up to 28,163 kilometers per hour, or 17,500 miles per hour. At those speeds, even tiny paint flecks can damage structures if they hit a spacecraft, because moving objects have kinetic energy. Whenever two objects come into contact with one another, they exert a force on each other for a short period of time. This is called a collision. About 95% of the white dots in this image are space debris orbiting Earth. The force of a collision causes energy to transfer from one object to another. The faster an object is moving, the more energy it will transfer. When a moving object hits another object, the force of the collision transfers some of the kinetic energy into the second object and into other forms of energy, such as sound. This is why collisions often make loud noises. The force can also transfer energy that changes the object's motion. If a paint fleck hits the International Space Station, the force of the collision transfers some of the kinetic energy to the space station. This transfer of energy is what causes damage, such as denting a window. If a more massive piece of space debris were to collide with the space station, it would cause more damage than a paint fleck. This is because a more massive object moving at a certain speed has more kinetic energy than a less massive object moving at the same speed. As a result, the massive object will apply a greater force in a collision, transferring more kinetic energy to the space station. Objects transfer energy during a collision because of action-reaction forces. Space debris can cause damage because it is moving so fast. More massive debris will cause more damage. Engineering in space. Engineers spend a lot of time thinking about how to protect the International Space Station and other spacecraft from space debris. Remember the STEM cycle. Scientists use experiments to gain knowledge, while engineers use that scientific knowledge and mathematics to solve problems by creating new technologies. For example, the space station is designed so that astronauts can move it out of the way of some debris. Another way that engineers protect spacecraft is with shields. Shields are physical structures that prevent space debris from reaching the spacecraft and causing damage. In order to design shields, engineers need to apply what they know about forces, energy transfer, and motion. Shields are designed to solve the problem of speeding space debris that can cause serious damage to an object, such as the space station or a spacecraft in space. In this example, the criteria might be that the shields must be able to withstand the collision force of space debris traveling up to 28,163 kilometers per hour, or 17,500 miles per hour. Available materials and cost are two common engineering constraints. Engineers need to research forces and motion so they know that when two objects collide, the force of that collision causes energy to transfer from one object to another. They also need to understand what momentum is. Momentum is the measurement of an object's mass multiplied by its speed. Before a piece of space debris collides with the space station, it has momentum that depends on its mass and the speed at which it's moving. When the piece of space debris comes into contact with the space station, its momentum causes kinetic energy to be transferred to the space station. The more momentum the piece of space debris has, the more energy it will transfer and the more damage it will cause. However, there are ways to reduce the effects of a collision. If an object's momentum can be slowed down before the collision, the force at impact will cause less damage. An object's momentum decreases when energy transfers out of it. This goes back to the conservation of energy. Remember that energy is never created or destroyed. This means that if energy is transferred out of an object, it will have less energy to transfer during a collision. Parachutes are a good research example of how slowing momentum reduces the amount of energy transferred during a collision. Parachutes work by slowing down the momentum of a person falling from the sky. They do this by increasing drag. As the force of gravity pulls the person down, drag acts in the opposite direction of the motion, slowing motion. The result of this is a much slower movement down to the ground because the person's momentum has decreased. By the time the person comes into contact with the ground, most of the energy has been transferred out of the system, made up of the parachute and the person. This is important because at the moment of impact, action-reaction forces will occur. When the person's feet hit the ground, that person applies a force to the ground. The ground will exert an equal force on the person. It's better for the person to hit the ground with as little force as possible. Parachutes reduce the force of impact by slowing momentum. The same concepts have been applied by engineers designing safety features in cars. People in a moving car all have momentum. If the car comes to a sudden stop, the people will keep moving inside the car because of inertia until they are stopped by an outside force. Airbags are designed to slow down a person's momentum gradually by using action-reaction forces to transfer energy out of the system. As a person's momentum pushes them into the airbag, air is slowly released out of small holes along the edges of the airbag. By the time the car comes to a complete stop, the airbag should be completely deflated. Engineers designing shields use these same scientific principles to try to slow down the momentum of the space debris before it reaches the space station or spacecraft. For example, some space shields are designed with layers that act similar to the bumper of a car. These bumpers absorb some of the energy from the collision. Because energy has transferred out of the system, the momentum of the colliding object decreases. As a result, there is less energy transferred to the car or spacecraft. This is a prototype of a space shield. I learned a lot reading Earth in Space, and I hope that you did too. I'll see you tomorrow with the next one. Bye.